Hello everyone. Today we will discuss an analytical problems on shear strength of PSC members. So let's start with first problem. The horizontal pre-stress at the centroid of a concrete beam of rectangular cross section 120 mm by 250 mm is 7 Newton per mm square and the maximum shearing force on the beam is 70 kilonewton. Calculate the maximum principal tensile stress. What is the minimum vertical pre-stress required to eliminate this principal tensile stress? So here it is given as rectangular section with 120 by 250 mm dimensions, and horizontal pre-stress what you are applying is 7 Newton per mm square and shear force of 70 kilonewton. We need to find out what is the maximum principal tensile stress and minimum vertical pre-stress required to eliminate that principal tensile stress. So this is the cross section you are seeing here. So 250 by 120. If you take the centroid of the section, it will be 250 by 2, it is 125. So Fx, it is horizontal pre-stress. F, it is a shear force 70 kilonewton. In terms of Newton, it is 70 into 10 power 3. Width of the section is 120 mm, and moment of inertia 120 BD cube by 12. It is 120 into 250 cube by 12. So we will get 156.25 into 10 power 6 mm power 4. So first we need to find out shear stress of the section. So for that, tau equals tau A, that is FA y bar by IB. So F is given 70 into 10 power 3. Area, remember here we are calculating with respect to centroidal axis or neutral axis. You are applying pre-stressing force at the centroid. So when you applied pre-stressing force, the tensile stresses will develop at the top half portion of the section. So we are considering only this hatched portion for the calculation of tau value. So here A means 120 is the width and 125 is the depth of the section we are considering into 125 by 2. So centroid of this hatched section with respect to centroid of overall section, that is 125 by 2 divided by I for overall section, and B width is 120. So we will get 3.5 Newton per mm square. So principal tensile stress, for tensile stress we need to consider negative, and for compressive stress we need to consider plus. So sigma 2 Fx plus Fy by 2 minus square root of Fx minus Fy by 2 whole square plus tau square. On substituting values, here Fy will be 0 because there is no vertical pre-stressing we are doing. Only horizontal pre-stress is given of 7 Newton per mm square. So Fy will be 0. Sigma 2 we will get principal tensile stress 1.4 Newton per mm square. So the next question is, to make this 1.4 Newton per mm square as 0, what should be the Fy value we need to apply, vertical pre-stressing force we need to apply for the section. So that's magnitude of vertical pre-stress Fy, so that sigma 2 should be 0. So on equating the same equation is equal to 0, so Fx plus Fy by 2 minus Fx minus Fy by 2 whole square plus tau square. So Fx it is given as 7 Newton per mm square, and Fy keep it as unknown only, and then substitute all the remaining values and simplify. On simplifying we will get Fy as 1.75 Newton per mm square. Since we have got positive value, that vertical pre-stressing should be compressive. Vertical pre-stress should develop compressive stresses. So if we get negative value, then it will be tensile stress. So if we apply vertical pre-stress of 1.75 Newton per mm square, then the principal tensile stress of 1.4 Newton per mm square will become 0. Next problem. A pre-stressed concrete beam section when subjected to a certain bending moment has a fiber stress distribution as shown in figure. The total vertical shear in concrete at a section is 2350 kilonewton. Find the principal tensile stress at the centroidal axis and at the junction of the web with the lower flange. So here, if you observe the figure, we have I section and stress distribution diagram is given. At the top, the maximum stress, fiber stress at top is 13 Newton per mm square, and at the bottom it is 0. And in I section, we need to find out principal tensile stress at centroidal section, centroidal axis, and at the junction of bottom web and flange. So first we need to find out what is the location of centroid for the given I section. Since it is unsymmetrical I section, we need to find out. So we have three rectangle components, a1 y1 plus a2 y2 plus a3 y3 by a1 plus a2 plus a3. a1 top flange 2400 by 400, and for centroid with respect to bottom, it is the height of the bottom flange is 900 and web height is 1000 plus centroid of the top flange 400 by 2, so it is 2100. Similarly, a2 width of the web 600 and depth of the web is 1000, and y2 900 thickness of bottom flange plus 1000 by 2 will get 1400, and a3 bottom flange 1200 by 900 and centroidal distance is 900 by 2 with respect to bottom. So on substituting here, we will get centroidal distance at 1266 mm from bottom of the I section, and for moment of inertia y bar minus y1 y bar minus y2 IBD cube by 12 plus a1 into y bar minus y1 whole square. So it is parallel axis theorem we are using here for individual component. BD cube by 12 plus a1 into y minus y bar minus y1 whole square plus BD cube by 12 plus a2 into y bar minus y2 whole square plus BD cube by 12 plus a3 into y bar minus y3 whole square. So on substituting all the values, we will get I as 1.54 into 10 power 12 mm power 4. So we have two questions here. First we need to find out at the centroidal axis and then at the junction of bottom flange and web. If you take centroidal axis, so we know it is located at the 1266 mm from the bottom. So tau we need to find out. F is given 2350 kilonewton. A y bar. So remember, here we are considering with respect to centroid. If you observe in this figure, so centroidal axis is at 1266 mm from the bottom. So we need to, if we want to find out the stress at the centroidal axis, means the portion of the section which is above the centroidal axis, that area we need to consider to calculate. So total it is 1266. So the remaining portion is 1034, that is total depth of the member is 400 plus 1000 plus 900, it is 2300. So out of 2300, 1266 is the portion which is below the centroidal axis, and above the centroidal axis we have 1034. So for that portion we need to find out tensile stress. So a y bar, if you take top flange area 2000 by 400 plus here it is a1 y1 plus a2 y2, like that we have considered. So a1 it is 2400 by 400 and a2 1034 minus 400 by 2. or you can take 1034 minus 200. So that will be y1 plus here the web portion above the centroidal axis remaining is 634 mm. The height of the web above the centroidal axis it is 634 mm and width is 600 mm. That area we have considered here, and for that centroidal height by d by 2, that is 634 by 2. On simplifying we will get ay bar value. Width of the web we need to consider as we discussed in case of introduction part. For flanged sections we need to consider width of web. So tau equals Fa y bar by Ib. On simplifying we will get 2.34 Newton per mm square as the shear stress. So Fx at topmost is fiber is given. If you observe this triangular figure, the topmost fiber is at under a stress of 13 Newton per mm square, but we need to calculate what is Fx at the level of centroidal axis. So by using similar triangle method we can calculate x1 here. So x1 by 1266 is equal to 13 by 2300, that is overall depth of the section. So on simplifying x1 we will get 27.15 Newton per mm square. So that will be treated as Fx. So principal tensile stress at the centroid, Fx plus Fy by 2 minus square root of Fx minus Fy by 2 whole square plus tau square. All in simplifying we will get principal tensile stress at centroidal axis we will get 0.7 Newton per mm square. So next, similar way, principal tensile stress at the junction of the web. Principal tensile stress at the junction of the web and bottom flange. So tau equals tau e, F equals, it is given value. Here we are considering the area of bottom flange only. So that means we are calculating at the junction of web and flange. So we are considering with respect to bottom flange only. So bottom flange size is 1200 by 900 in this figure, and if you take the centroid 900 by 2, so with respect to centroidal axis it will be, where it is, 1266 minus 900 by 2. With respect to centroidal axis we are taking the distance. So ay bar we got. B again width of the web for flanged section, tau Fay bar by Ib. So tau we will get 3.24 Newton per mm square. Sorry, it is 2.24. So from similar triangle, x2 by 900 is equal to 13 by 2300. So the same triangle we need to consider at the level of bottom flange and web. Here it is, bottom flange and web. At the level of bottom flange and web is, that means from bottom it is above the 900 mm in this triangle. So on simplifying we will get x value 5.08. So Fx at the level of junction between bottom flange and web is 5.08 Newton per mm square. So again principal tensile stress at that junction we need to consider this same equation, but substituting Fx with and tau as obtained at that level. So we will get principal tensile stress is 0.85 Newton per mm square. Next problem. A post-tensioned beam of rectangular cross section 200 mm wide and 400 mm deep is 10 meter long and carries an applied load of 8 kN per meter UDL, or uniformly distributed load, on the beam. The effective pre-stressing force in the cable is 500 kN and the cable profile is parabolic with zero eccentricity at the supports and maximum eccentricity of 140 mm at the center of the span. Calculate maximum and minimum principal stresses at the support. So here remember, the beam is carried with UDL of 8 kN per meter. It is a rectangle section only. Effective pre-stressing force is 500. cable profile is parabolic with zero eccentricity at support and eccentricity of 140 mm at midspan. We need to calculate maximum and minimum principal stresses at supports. Based on the sign, we need to decide whether it is tensile or compressive. So this figure shows cable profile, cross section of the beam. So overall depth of the beam is 400. So centroidal axis will be at the 200 mm depth. If you take the support reactions for UDL throughout the span, it will be WL by 2 on either side, either supports. So that will be support reaction. So first let us take moment due to dead load and live load. Sorry, not moment. Total load we will consider. So live load is 8 kN per meter and dead load is 1.92 kN per meter. 0.2 by 0.4 is the cross section and 24 is the density of the concrete. So total we will get 9.92 kN per meter as the total load. Area of cross section and P, it is given pre-stressing force, I value BDQ by 12. So bending moment due to UDL for simply supported beam at support, it will be 0 as we know. And pre-stressing moment due to pre-stressing force at support, again since eccentricity is 0, bending moment due to P at support, it will also be 0. So if we have eccentricity, then PE by I will come, but here we have 0 eccentricity, it will be 0 only. So first we need to find out what is the slope of the cable at support. So at support, to find out slope, we need to consider first parabolic equation y equals 4e star L by L square into Lx minus x square. So we need slope means first derivative, it will be treated as sine theta. So dy by dx, on simplifying we will get 4e star L square by L square into L minus 2x. At support, x will be 0. So substituting x will be 0 and simplifying we will get slope of the cable as 0.056. So effective shear force at support, WL by 2 is the support reaction. Here P sin theta is, if you observe the figure, 500 kilonewton, it is inclined force. So theta, we have calculated slope of the cable, so that is 0.056 with respect to horizontal axis. That slope is calculated with respect to horizontal axis. On resolving, horizontal component will be cos theta and vertical component will be sin theta. So since we are calculating shear force, we are going to consider only vertical component. So WL by 2 is in upward direction and P will be in downward direction. Yes. So we have considered negative. WL by 2 minus P sin theta. On substituting, we will get pre-stressing force 21.6 kilonewton. Sorry, shear force in at support section, it is 21.6 kilonewton. Tau, again same, half of the area we need to consider. So now the size of the beam is 200 by 400, half of the portion means 200 by 200. So again with respect to centroidal axis, the centroid of shaded area in this figure is again 200 by 2. So that we need to consider into 4. So it is 4 into 10 power 6 mm cube. So that is AY bar. B is 200. I, it is for overall section. Remember, AY bar will be for shaded area and I will be for total area we need to consider. Tau equals FAY bar by IB. On substituting we will get 0.407 Newton per mm square. Then Fx equals, here we need to calculate both maximum and minimum principal stresses. So we need to consider both plus or minus. So first we need to find out Fx. So here eccentricity at support is 0. So PE by I into Y will be 0. M by I into Y at support moment of with respect to loads, dead load and live load is also 0. So we will remain with only P by A. So Fx is 6.25 Newton per mm square. Then principal tensile stress sigma 2. On substituting we will get 0.0264 Newton per mm. Next problem. A beam 300 by 800 in cross section is simply supported over a span of 12 meter. It carries a UDL of 24 kilonewton per meter in addition to its own weight. The beam is pre-stressed with a parabolic cable which has maximum eccentricity of 300 mm at midspan and 60 mm at supports above the centroid. Determine the principal tension at 100 mm below the centroid across the section which lies at 2 mm from left support. Effective pre-stress in the cable is 800 kilonewton. Assume density of concrete as 25 kilonewton per meter cube. See, here we have some different condition here. So beam size is 300 by 800 and span of the beam is 12 meter. UDL of 24 kilonewton per meter in addition to its self weight. We need to find out self weight also. Cable profile is parabolic with eccentricity of 300 at midspan and 60 at support. Then determine the principal tension at 100 mm below the centroid across the section which lies at 2 meter from the left support. Effective pre-stress is 800 kilonewton. Common density of concrete 25 kilonewton per meter cube. So this sentence, determine the principal tension at 100 mm below the centroid across the section which lies at 2 meter from left support. So in our figure, if you observe from left support, we need to consider the section at 2 meter away from left support. In that portion, in that section again 100 mm below the centroidal axis. So 800 is the overall depth of the section, so 400 will be centroidal axis. So in 400 we need to consider 100 mm below the centroidal axis. That means from bottom we need to consider 300 mm height, that area for calculation of stress. At that particular level we need to find out the tension stress. So that area of shaded portion or hatched portion will be 300 by 300. So live load, it is given 24 kilonewton per meter. Then dead load, cross section 0.3 by 0.8 into density is given 25, 6 kilonewton per meter. So and adding we will get 30 kilonewton per meter as a total load. Eccentricity 300 at midspan and 60 above neutral axis at support. So on total depth of the cable is 360 mm. Area of cross section 300 by 800. Pre-stressing force, it is 800 kilonewton. Moment of inertia I is VDQ by 12. Now we need to find out at a distance of 2 meter from left support. If you consider midspan, it is 6 meter, but we need to concentrate at 2 meter from left support. So since it is a parabolic cable, first we need to find out what is the depth of the cable at that particular section, that is 2 meter away from left support. So at that section, what is the depth of the cable, that we need to find out first. So on considering parabolic equation, 4 E star by L square into Lx minus 2x, since we are calculating depth of the cable at 2 meter, substitute x is equal to 2. Here we are calculating depth. Okay. So on substituting we will get y is equal to 0.2 meter, that is 200 mm. So here we are having eccentricity at top as well as at bottom. Eccentricity above the neutral axis as well as below the neutral axis we have. So above neutral axis it is 60, below neutral axis it is 300. So if you take overall depth with respect to support, overall depth of the cable at 2 meter distance we have 200 mm. So eccentricity is with respect to centroidal axis. So 200 minus eccentricity above neutral axis 60. So actual eccentricity of cable below the neutral axis at 2 meter distance from left support is 140 mm. So again we need to consider the same equations because we need to calculate slope also. So again consider same equation to calculate slope. First derivative of the parabolic equation will give us the slope. So dy by dx for E star by L square into L minus 2x. So x equals 2 meter again. Tan theta or is almost equal to sin theta. So at a 2 meter distance the slope of the cable is 0.08. Then shear force at a distance of 2 meter from left support, WL by 2 minus W by 2. So this is for load, WL by 2 minus W2, W into 2. So this is 120 kilonewton. So this is with respect to dead load and live load. Now bending moment due at the distance of 2 meter from left support with respect to dead load and live load, WL by 2 minus 2, WL by 2 into 2 minus 30 is the load into 2 into 2 by 2 for UDL. So we will get 300 kilonewton meter as the moment with respect to dead load and live load at that particular 2 meter section from left support. Then effective shear force F equals 120 minus P sin theta. P sin theta. So here 120, it is shear force at that particular section we need to consider. So in previous problem we have directly considered WL by 2 minus P sin theta because we are calculating at exactly at the support. But here we are moving 2 meter away from the support. So at that support, at that section 2 meter away from the support, what is the shear force? That is 120 kilonewton. So 120 minus P sin theta, vertical component of precessing force at that particular section. So at that particular section the slope of the cable is 0.08. So P is 800 into sin theta slope is given 0.08. On simplifying we will get 56 into 10 power 3 Newton. A Y bar. So 300 is the width of the section, depth 100 mm below the neutral axis or centroidal axis, means the centroidal axis is located at the 400 mm. So 100 mm below the centroidal axis is remaining portion we need to consider, that is 300 mm. So 300 into, with respect to centroidal of the section we are calculating Y bar, so 100 plus 300 by 2. So it will give 22.5 into 10 power 6 mm cube. So tau FA Y bar by IB. So F we have calculated, A Y bar we have calculated, I is the moment of inertia for overall section and B is the width of the section of 300 since it is a rectangle. So tau equals 0.328 Newton per mm square. Now to calculate Fx, P by A plus PE by I into Y minus M by I into Y. So Fx P by A plus PE into I into Y. So here Ex means we are calculating stress at 2 meter away from the centroidal left support. So at that particular point eccentricity we have calculated it is 140 mm. So Ex will be 140 into at the level of 100 mm below the centroidal axis we are calculating the stress. So Y is equal to 100 minus 300 into 10 power 6 by 1.28 into 10 power 10 into same 100 mm we are calculating at the section. So on simplifying we will get 1.864 Newton per mm square. So principal tensile stress Fx plus Fy by 2 minus square root of Fx minus Fy by 2 whole square plus tau square. So here Fy there is no vertical stress, so Fy will be 0, and on substituting and simplifying we will get principal tensile stress as 0.056 Newton per mm square. So this is all about today's problems. In next class we will discuss few more problems on the same topic. Thank you.